All right. Hello, everyone. Today we'll be going over the we reviewing some stuff for the test because basically there's nothing in this week's homework that requires RStudio or R. There's just some probability calculations. So we'll just be going over everything in general that you'll need. We'll start with some simple things, and this is the agenda for today. We'll just go quickly over everything that we've been through up to today, so that you can be ready for the test. For the math part of the review, that'll be Friday from 3 to 5 p.m. So this will be more the R part of the test. So in the test, you'll be asked to load an R data file. So that's a very simple thing to do. So I'm gonna show you how to do this. It's very easy. So let's say that I have nothing in my workspace. So let's say as you can see here, the global environment is empty. And what I'm gonna do now is I'm gonna load an R data file. So basically, where you are, let's say I'm here in this directory right now, stat309, and I have in the same directory I have iris.rdata. So you have that. I can just run this function, load iris data. So just to be sure you have the name correct. And if I run this, I'm going to have it here in the environment. So the way I did this is very simply, so let's do this once more. I'll show you what I did. So for example, let's say I have some data set iris in my work environment. I can save this. So I'm telling it to save iris, this data here, and I'm gonna call it iris.rdata. I can call it whatever you want. I can call it my saved data.rdata. If I run this, now I should have it here. As you can see in the folder, I just saved it. I have it my saved data.rdata in here. So I'm gonna remove everything with this command so that it's empty. So you can see here it's empty. I have nothing, and then then if I try, oh, interesting, and then that shouldn't work. So I can load it here. I just need to put the correct name, my saved data.rdata. There it is, and I can load it, and I have it. Okay, so
what do you do before you put in load iris? So when I put that in, it just said it came up with error.
No, so before that you can do this. So this is not something you should do right now. I mean, you don't have to do it. I'm just showing you everything you'll need for the test is this line here, load something.rdata. So basically when you'll be doing the test, you'll just be saving your rdata file. I mean, I think you'll just click download in the test, and then you'll have it in your. So here, if I look at files, this is everything I have here. So it should be here. And then if it's here, then you can just do load and then write the name of the file and .rdata, and it'll load in your environment. So I just did that for iris as an example. You don't have to repeat. This.
If you just have like import data set, is that like the same thing?
No, it's not the same thing. No. So the import thing you're doing in the homeworks is when you have a CSV file or an Excel file. This is different. This is not the same thing. So this is something else. So basically, this is all you need to remember. This line here. Just load and give it the name. Yeah. Okay. So as you all know, I'm guessing you all know that R can be used as a calculator. You can also use it as a way to, if you want to, for example, add a number to the whole vector. Let's say I have the vector 1, 2, 3, right? This is my vector, right? 1, 2, 3. So if I want to add 2 to all the numbers, I can just add 2 to the whole vector. It's going to automatically add 2 to every element of the vector. So that is kind of useful. So for example, here I saved it as my vector. You can see it here, it's 1, 2, 3. If I run the next line, 2 plus my vector, that's 3, 4, 5, and I can save that to my vector. Now the values are going to change. So here it's 3.5 now, 3, 4, 5. I can also square it to get the squares. Now there's a few ways to do breaks for histograms, for example. One way would be to do it manually, like this. So as you can see here, breaks is my vector at 0, 5, 10, etc. Now I can also do it like this. I can say from 0 to 50 by 5. So this is going to do the same thing. As you can see, breaks 2 is the same as breaks 1. It's 0, 5, 10, etc. I can also change so if I put names here, it doesn't actually matter the order in which you do it. So, for example, the first argument is from to by, but if I tell R the names, I don't have to order them. So, in case you don't remember which argument goes first, which goes second, if you just give it the names, it's still the same. So, if I run this line, I still get the same. See, breaks 3 is the same as the other two. So, I can just change the order. But if you don't give it the names, for example, here, see, I have to do it in the way that it's supposed to be done. And if you forget, you can always do question mark and the name of the function, and then here it'll tell you. So sequence, it says from, to, by, etc. And there's some other stuff, but you don't need. You just need the first three things. So this is very useful function to have in case you're lazy and don't want to write the whole vector. Okay, so you probably know that the mean can be checked like this, right? So just take a column of vector. So irises are my data. So once again, just to show you, so this is my data. I'm gonna take this column, sepal.length, and I'm gonna take the mean of the column, and that's this. So that should be equal to this if I do it manually. So if I sum up all the values and divide by the length, I should get the same thing, thankfully. So another thing would be the quantile, which might be useful. This gives you the median, the first interquartile or first quartile, I think it's called, the third quartile, and the maximum and the minimum. So this is the minimum and this is the maximum. Now, if you have some NAs, for example, what was it called? My vector? Oh, my vector. My bad. So this is my vector. So let's say that. So now I added an NA value, so not a number, to the vector. So that's like, so if this is the irregular vector, so the one that I called with.na looks like this. I just added an NA value at the beginning of the vector. Now if I take the mean, automatically it gives me NA, but you can always write this at the end. So for almost every function that does anything, for example, linear regression does this automatically. You don't have to add. If you have missing values, it's just going to skip them. So for the mean, it'll give you NA, but if you add NA.rm, which means just remove the NAs when you're calculating the mean. If you set that to true or T, any of the two, if I do this, then I'll get the mean. Histograms, again, I'm just loading the data, which I have already. Okay, so for a histogram, I can, let's see. Okay, so this will be a histogram of the length for these flowers. So I give it the breaks. I made it manually so that it goes from 4 to 8 and goes by 0.2. This is what I manually did. I don't have to do it. I can do it without. It'll just look different. So this is how it looks normally. You can also do the frequency if you add frequency equal to, instead of the frequency you can use the probability. So if I do frequency equal to f, I get the probabilities here. And right equals to f will just change so that the value, for example, if this is 5, if I have a value that's 5, it can either go in the left bin or on the right bin. Just right equals to f, of course, just means it'll go to the left bin. This doesn't really, I don't think you'll need this for a test, but just in case. And now z-scores are something you'll probably need. So a z-score is most simply, if you have a value x, you can subtract the mean, let's call it mu, and then divide the whole thing by the standard deviation. This will give you the z-scores. So let's say I have this vector, my vec. Now this is the whole vector. It has 150 values, all the lengths. I can subtract the mean and divide by the standard deviation manually. So this will be normalized. And now if I look at the normalized vector, it has all the values centered around 0. Exactly what the z-score entails. Now, you can either do that manually, or you can also use the p-norm function if you're looking for a probability. For example, the p-norm function, by default, uses a mean of 0 and a standard deviation of 1. So when if I give it the normalized values, it can give me the probability. So these are the probabilities. Now, I can do that with the original vector before standardizing it, if I just give it the mean and the standard deviation here manually. So these two will give the same answers. See, so I can either do it manually first to normalize them like this, like I did here, or I can just give it the original vector and just tell it that this is the mean and this is the standard deviation. Both of these will work. As you can see, they both give the same answer. So when you're working with data frames, a few functions are very useful. So first, get the dimensions of the data. If you do dim of your data frame, which is iris in our case, you just get 150 rows and 5 columns. That's very useful to know. Also, you can just do n row or n col. Again, the mean, we went over this. Okay, box plot. Again, this is very, you just need to run the function box plot. It'll just give you, if there are any outliers by the, I forgot the name of the method. I think it's 2-key method maybe. I don't remember what it was. But, there is a method for it to calculate outliers. If there were any outliers, they would have been shown here in X marks. Stem and leaf plot, of course, you know. Shown the stem function. Now for something more important, so let's say I want to do linear regression. We're going to use the iris dataset again. So for those of you who want to follow this, you can just do data iris. This will load up the iris dataset, and you can look at and run these 2 lines, and you'll have the iris dataset in your environment. And I'm going to take for X, so I'm going to do a very simple regression. For X, I'm going to take the sepal length, and for Y, I'm going to take the petal length. So I'm going to try to predict the length of the petals by the length of the sepals. So I'm just taking the whole vector, and I'm going to plot it just to show you how it looks like. So this is what it looks like. X is our sepal length, and Y is our petal length. So as you can see, there is some correlation here, right? But I think it's not very linear. I mean, in my opinion, there's a weird thing. Because the dataset has 3 different species. 2 of the species are over here, and 1 of the species over here. So you can see this species is very different. So plotting a line is not going to be very good. And we're going to see how it looks like and how we can diagnose this. So to run the linear regression, you just take your target variable, which is y, tilde, and the other variables or variable that you need to do. So this is, now we ran the linear regression, and now I can plot the line. If I do AB line, that should plot the line. And here it is. This is the line that the linear regression found. As you can see, it's not very useful. So to find out information about our model, we just do summary model, and it gives us everything that we need to know. So the intercept has been estimated to -7. The coefficient in front of x is estimated to 1.85. This is the standard error of the regression. So these are the t statistics. The p-value is over here. As you can see, it's very small, so it means it's highly significant. And you have the r-squared. So always use the multiple r-squared, not the adjusted r-squared. So in the homework or in the test, always use the first value, well, multiple r-squared. To get the correlation coefficient, of course, you know that you just need to take the square root of the r-squared to get the correlation coefficient, which we'll show later. Now, for now, I'm just gonna show you the residuals, and so these are the residuals. The residuals are the observed value minus the predicted value. So what we observed minus what we predicted with our model, and we can plot the residuals like this to show you what they look like, and this is what the residuals look like. As you can see, they're not actually, they don't look very normal or random. So if they look normal, they should be everywhere in this plot. So as you can see, there's a gap here and there's a gap here. They're not equal. That's because if you remember from the previous plot, as you can see here, you can easily see why that's the case. So here the line goes over most of the data at the beginning, and then it goes under most of the data here. So that's why the residuals don't look well. So you can also plot the residuals against the x values, against the actual values. Sorry, not age. X. My bad. Let's plot it. Okay. Right. So this is x versus residual. As you can see, they look very strange. So if you plot the x values versus the residuals, this is the rest of this line is just to give it names. You don't have to write that. You can just do it like this. So if I plot x and resid, I get this. This is very strange looking. They should be centered around this line here. They should just go above and below, equally likely. Now, what I'm gonna do here is, since we have the data set, I'm gonna show you what I'm gonna take only these values. Let's say I'm gonna take the values from here and upwards. So I'm just gonna take the latter half of the data set, which should look very normal. So I'll just do 75 to 150 just to take the latter half. I'm gonna plot it again. So here we have only the latter half of the data set, which looks much better. And now if we plot a line, we should be looking at very much nicer residuals. So let's run the model again and show you the line. Now you can see the line goes equally through the data set. So this is what we want. So this is what a normal regression looks like, not the thing we had before. Again, summary, we can look at the t-value, the p-value, and now we plot the residuals with the plot function. They look normal, but the key thing is here, if you plot this line, this before that looked very strange. Now here, if I plot the line, this is what it looks like. So this is what you're looking for. So a normal residual plot, when you plot the x values versus the residuals, you should get this. As you can see, there's no pattern here, whereas before we had a very strange pattern. Now, one useful thing is let's say I want to take the correlation of my data. So I can. So there are 6 different correlations here. There is between this and this, the first and second, the first and third, first and fourth, second and fourth, and third and fourth. There's 6 different values. So I'm gonna take these 4 columns, so without the 5th one, which I can do either like this, 1, 2, 4, or I can just say don't take the 5th column, -5. So I can do correlation of my data set and I can get the values here. So this is sepal length versus sepal width here. So you can see I've got a table of correlations, which is very useful if you don't have to run for each pair. Now I can also show you directly the correlation between my two. So x is this one, sepal length, and y is pedal length. I can just do the correlation directly. Let's call it r, and that's 0.842, and r squared is 0.71, and that should be the same as the correlation here. And yes, so it's 0.710. If you round it here, we'll get a 1 here, so it's 7101, and here the multiple r squared is 7101. So basically you have the r squared. You can either do it through the linear regression, or you can just take the correlation, which is 0.84, and then square it, and then you get the r squared. We'll go just quickly over the table and prop table again, just to show you. This is the Titanic data set. For those of you who don't have it, so if this gives you an error, this line library Titanic, you can just run this line here, install.packages Titanic, but give it quotes here. So no quotes here, but quotes in the install.packages. Now this data set is we'll just take these 4 values, 4 columns: survive, p-class, sex, and age. And we can look at some. I'm gonna rename them here, so that you don't have to do this part. This is just easier so that we can call the classes first, second, and third instead of 1, 2, and 3. So when I do table, I can look at the survival and the class of the ticket holder. So for example, in first class we can see that more people survived, a lot more people survived than perished, but in third class most of the people perished, unfortunately. All right, so let's save this to a table called tab. And to get to get different indices in the table, of course, I can just take the second. For example, to take the number 87, I can just take the second row and the second column, and just run this line, tab 22, and give me the number. I can also use names. So if they are named, I can also use the names. For example, this will be survived and second. So if I do tab survived and second, I should get the same number. Let's see, a bar plot. You can just take the bar plot. So this will give me. This here takes the survived row and takes all the columns. So in this table, it'll take these 3 numbers. So if I take these 3 numbers and give them to a bar plot, I get this here, which corresponds to the numbers. So 136 is over here, 87, and then 119. I can also do a pie chart, the same way as just changing the name. Again, it looks okay. Prop table is something that will be very useful, I think. But if not, you can always do it manually. So prop table will give you the joint probability. So I think you went over probabilities, which means you should know the difference between a marginal probability, a conditional probability, and a joint probability. So for example, a joint probability here means what is the probability that the passenger is both first class and perished. This is a joint probability. Then we would have the marginal the conditional probabilities. So here I'm gonna sum up by columns. So you can see here each column sums up to 1. So that means that now I can look at what is the probability that if it sums by columns, then I have different conditional probabilities for first, second, and third class. Which means, for example, given that the person is first class, what is their probability of survival? And that's 0.629. And if they're second class, what is their probability of survival? That's 0.47. And if they're third class, it's 0.24. This makes intuitive sense, right? We saw from the numbers before, so just to show you again. This is the table, right? As you can see, if you're third class, your chances of survival are very low. It's 119 divided by the sum of these. And if you're first class, your survival chance is much better. So that's prop table. So the 2 means you sum by columns, and that's why the columns sum to 1. If you want to sum by rows, you just write 1 instead of 2. And here here you can ask the other question. Let's say that the person survived. What is the chance that they are first class, second, or third class? So this is the other conditional probability. Now I can use a bar plot here to show you what is the survival probability given the different classes. So I can just do a bar plot of the prop table from before. And if I do that, we can see first, second, third class. Let me add the legend. So that's, yeah, this looks bad. Okay, so remember that survived is the white, the lighter region, and perished is the darker region. So without the legend, as you can see, the survival probability is much better for first class and much lower for third class. You can also do mosaic plot. Oh, and if you want to do it the other way, you can turn your table here. So T transposes the table. So if this is my table here, I can do T to transpose it like this, and it'll transpose it. You can see now the rows are the columns and the columns are the rows. If I do that and run bar plot, but instead of the table here, I'm transposing it, I can, without the legend, if I do this, then now I can look at what is the probability that a person is the first class if they perished or if they survived. So this is the other bar plot you can draw. You can also do a mosaic plot. Here, for mosaic plot, usually you don't give any numbers. You don't give it numbers here, so you just do a joint probability. So this is what it looks like. This gives you the joint probability, someone being first class. So this is the amount of people that were first class and perished, the amount of people that were first class and survived, etc. Now, if I have a data frame like this, and I can look at the, let's say I want to look at the people who survived only. So this will be this. I'm writing head here so that I get the first 6 rows, 6 elements only, because I don't want the whole vector. I can, if I remove the head, I'll just get the whole vector, which is long. It's 900. So I don't want it. That's why I have head here. But this gives you so true is where the person survived and false where it didn't. But the good thing is I can take the mean of this vector, and the true counts as 1 and false counts as 0. So if I do mean, I will get the proportion of people who survived. This is just in general, without looking at class or sex or age. So here I can get the joint probability manually. So let's say in the data frame, I want the people who are first class and the people who did not survive. And I sum those up and divide by the row. So this should be the probability of the passenger being first class and they perished. If I do prop table, I should get the same number. So first class and perished gives you this number, which is exactly the same, thankfully. Okay, so this has been a short overview of what we covered. And if you have any questions, go ahead.